and move on to another important discussion as to what exactly is the role of this Lagrange multiplier. So far we haven't told anything about this constant lambda, not in this example, but in general. So what is the role of lambda, right? So let me briefly discuss the role of lambda. So the role of lambda, right, which is our Lagrange multiplier in isoperimetric constraints, right. So notice that in this example, in the previous example, lambda was the radius, right. So lambda definitely corresponds to some physically or geometrically important parameter in the problem, right. So lambda corresponds, we see that lambda corresponds to a physically or a geometrically important parameter. Now we are going to exactly highlight what exactly is the importance of this Lagrange multiplier lambda, because noting down the significance of lambda will help us to look at the problem from another point of view, right. So let us look at the functional again. So consider my functional j of y, which is now, so I am now including the isoperimetric constraints within this functional. So we consider this functional j of y from integral x0 to x1, which is f of x comma y prime, plus lambda times L by x1 minus x naught minus g of x comma y prime, right, times we see that this is integral of dx. Okay. So note that, so what we have done is, this is my isoperimetric constraint that is now included in my functional, isoperimetric constraint included in my functional. So then what we have is, let us look at the derivative of j with respect to L, right, L being this parameter in the system. So when we do that, since this quantity or this integrand that we have is continuously differentiable up to second order, we can very well take the derivative inside the integral, right. So this is my derivative with respect to L of the following quantity f plus f minus lambda times g plus lambda L by x1 minus x naught, right. So what I have is the following, right. So this one is integrated with respect to x. So then we can use some chain rule. Let me denote this quantity by capital F, and we can use chain rule by showing that this derivative becomes del f del y times del y del L plus del f del y prime times del y prime del L, and note that my quantity lambda can also be a function of L. So lambda can be in general a function of L, right, because L again is a parameter, but it is a constant parameter, right. So which means that we can also have derivatives of this form, del lambda del L times, this is now multiplied by L over x1 minus x naught, because we have differentiated with respect to L with respect to L of lambda, and minus lambda also appears here. So minus integral of g dx, right, and then what we have is, we also have an L sitting here. So once we differentiate, and integrate from x1 to x0. So, this becomes, this is integrated with respect to x, plus lambda is outside the integral, right, because of the derivative of L with respect to L, right. Okay. So, then what we have is, notice that when we integrate this quantity, integrate by parts, we integrate this quantity by parts, we can slightly simplify this expression, right. We see that we get integral from x0 to x1 del y minus d dx of del f del y prime of f, right, of f times del y del L times dx, right. And then we also have plus del lambda by del L, that is the second quantity, of L minus integral of g dx, and then so this is under integral, right, dx, well, dx is already there, and then plus the constant of integration lambda, right. So, notice that f, so this is going to be 0 because y is an extremal, and it satisfies Euler Lagrange equation with my integrand f, right, and this is also equal to 0 because of the isoperimetric constraint, right. So, we have that y is an extremal because, so finally what we get is that everything inside the integral is 0 because of the Euler Lagrange equation and the isoperimetric constraint, and the only quantity that survives is the quantity outside the integral, which is equal to lambda, or so what we get is that del j del L is equal to lambda. So, what we have shown is that lambda is the rate of change of the functional j of y with respect to the parameter L, Now, or there is another way to look at this result. It shows a duality of the isoperimetric problem. So, which means what we are trying to show is the following. What we are trying to show is that there exists a duality for isoperimetric problem. There exists a duality for isoperimetric problem, and note that, so what this means is that we are trying to extremize j subject to I. Let us say we are trying to minimize j with respect to I, minimize j subject to I as the constraint. This is also equivalent to saying that we are trying to maximize I subject to j as the constraint, right. So, we can flip the role of I and j for isoperimetric problem, or notice the following. So, to see this, to see whatever I just now said, to see that, note the following. Note that suppose that my lambda, my Lagrange multiplier is non-zero, then for any extremal y, I have that f is f minus lambda g. For any extremal y, my capital F is f minus lambda g is also an extremal for g, which is g minus lambda hat f, where my lambda hat is 1 over lambda, right. So, which means that the same Euler Lagrange equation holds for the extremal y with the function f or with the function g, right, with the roles of lambda reversed. Instead of lambda, now we have 1 by lambda for the other situation. Now, how is this possible? It is quite simple to see that, because note that j minus lambda of I. So, this is my functional, and this is my constraint. This is my isoperimetric constraint. Note that this is also equal to minus lambda of I minus lambda hat j. So, as if we were to extremize the constraint on the left hand side, it is saying that we are extremizing the constraint on the right hand side with the roles of I and j reversed, right. So, which means that the minimum of f, the minimum of integral f dx from x0 to x1 is equal to the maximum of integral g dx from x0 to x1, and this can be vice versa, right. Okay. So, what have we got here? So, let me just state this duality in the form of a theorem. So, the theorem says the following. So, this is theorem number 11. So, it says that suppose y produces a minimum, respectively a maximum, right, value for the functional j subject to I of y is equal to L, and lambda is not 0, right. Then let k be equal to j of y, then y produces for minimum. Now, y produces a maximum for the other problem, and for maximum y produces a minimum respectively, right. So, the roles are reversed. So, y produces a maximum for I subject to the constraint j of y is equal to k, right, subject to the constraint. So, now the constraint is j and the functional is I. Now, there is, to quickly look at what this result means, let us again revisit the problem of catenary very quickly. So, what was the problem of catenary? So, for example, in the problem of catenary, we were trying to minimize the potential energy subject to the length of the cable being fixed. There is another way to state the catenary problem. We are trying to maximize the length of the rope subject to the fixed potential energy, and that is how the roles are reversed. So, in the catenary problem, we were saying the catenary is a curve. It is a curve along which the potential energy is minimum subject to the potential energy is minimum subject to fixed cable length. The potential energy is minimum subject to fixed cable length, and this is also equivalent to saying this is the curve with maximum cable length subject to fixed potential energy, right. Okay. So that concludes the discussion on the role of the Lagrange multiplier. So we can now proceed with the generalization of the isoperimetric problems. Okay. So let us look at the generalization of isoperimetric problems. Okay. So let us look at the different cases. We could generalize in several different ways. The first case could be for functionals with integrands having higher order derivatives, right. So problems with higher order derivatives. We see that consider g of y equal to integral from x0 to x1 j of, well, let us look at this functional f of x comma y prime y double prime dx. Okay. And we have the isoperimetric constraint. So subject to the constraint integral from x0 to x1 g of x y y prime y double prime dx. Okay. So here we assume that f and g are smooth, having all the necessary derivatives required for the necessary condition or the Euler-Lagrange or Euler-Poisson equation. Okay. So then the necessary condition in this case, I am not going to go into the derivation of the necessary condition, but the necessary condition in this case is the Euler-Poisson equation, which tells us that the extremal need to satisfy the following equation: partial y prime minus partial x of partial y prime plus partial y, right, of f is equal to 0, or where f is equal to f minus lambda g, right, where lambda is a constant, Okay. So we have given the generalized version of the isoperimetric problem for this case of generalization. Okay. So the generalized version of the Euler-Lagrange equation for this case. Okay. So then let us quickly look, well, we can look at an example in this category, but let us there are few more points that I want to highlight before we look at an example. So the first issue that I want to highlight, that lambda or Lagrange multiplier exists, or Lagrange multiplier in this generalized scenario exists, provided y is not a rigid extremal to I, right. It is not an extremal for the functional I. So we are trying to remove the rigid cases or the abnormal cases, looking only for the normal cases here. Okay. So lambda exists provided that y is not an extremal, it is not an extremal for the functional I, right. And we can, another issue to highlight is that we can extend the result to higher order Euler-Poisson equation, that is third derivative, fourth derivative, and so on and so forth. And finally, how about the abnormal case? For the abnormal case scenario, we need to, like we have always done, we need to introduce two Lagrange multipliers, lambda 0 and lambda 1, where that includes the case where y is a rigid extremal, that is not included in discussion 1. So, in this case y is a rigid extremal. When I say rigid extremal, it means that y is an extremal for the isoperimetric constraint or I of y, right. So, the abnormal case can be solved by introducing set of two constants or two Lagrange multipliers, lambda 0 and lambda 1. Okay, so let us quickly look at an example in this category. So, the example I have in mind is the following. So, we have the given functional integral of 0 to 1 of y double prime square dx subject to, so we are trying to extremize subject to I of y, which is integral 0 to 1 y dx, right. This is equal to 1, right. So, this is my isoperimetric constraint with fixed value, and I also have the boundary conditions. Y of 0 is equal to y of 1 is equal to y prime 0 is equal to y prime 1 is equal to 0. Okay. So, 4 sets of boundary conditions. So, note that this is the extremal to this setup is going to be the solution to the Euler-Poisson equation subject to these 4 sets of boundary conditions. So, I have f is y double prime square and my g is y, right. So, what I have is, now before even I solve for the extremal, we just do not know whether we have an abnormal problem or not, or whether y is a rigid extremal or not, right. So, we do not know. So, we want to eliminate the case of rigid extremal. So, let us check for rigid extremals. So, we check for rigid extremals, right. Now, suppose so if I have any rigid extremal, then y will satisfy the Euler Lagrange equation with so or y will be the extremal to this isoperimetric constraint I of y, right. Any rigid extremal will satisfies the Euler Lagrange equation with the function g, right. This is set equal to 0. So, any rigid extremal satisfies the Euler Lagrange equation with this set equal to 0, where g is this function, which is the function for the integrand for my isoperimetric constraint I of y, right. So, let us see what happens. Note that g is purely a function of y. So, the first quantity is 0 and the derivative of g with respect to y is 1. So, which means that I get minus 1 is equal to 0, or I get a contradiction here, right. So, which means that there are no rigid extremals to the problem. So, we are in good shape, we are in the case of normal problem category. So, we can peacefully solve for the extremals. Okay. So, let us look at the Euler-Poisson equation. So, consider my Euler-Poisson equation with capital F equal to f minus lambda g, and I see that after plugging in f is equal to f minus lambda g in the Euler-Poisson equation, I simplify to the following ODE: 2 times y fourth derivative of x minus lambda is equal to 0. So, I am just writing the final form of the condition, necessary condition that the extremal satisfies. So, from here I can quickly find that the solution is y of x is lambda to the power 4 factorial x to the power 4 plus c3 x cube plus c2 x square plus c1 x plus c0. So, there are Ci's and lambdas are unknown, right. So, there are 5 of unknowns in total, but we have also the boundary condition y. So, we use these boundary conditions. Y of 0 is y of 1 is y prime 0 is equal to y prime 1 is equal to 0. So, we have 4 boundary condition plus we have the isoperimetric constraint that makes it 5 conditions for 5 unknowns, and hence this system is fully determinable, and students are asked to check that the system can be fully solved, and they should find the values of lambdas and Ci's as an exercise. So, I am just going to write the final answer. The answer is, please check that the answer that we get is the following. So, y of x is 30x to the power 4 minus 60x cube plus 30x square. Okay. So, this is what the extremal that we get.